All right. Right now, I would like to briefly introduce what is the so-called integrated circuit. Yeah, the history and also hopefully the future. All right. And this is some kind of reference. I got help. Yeah. To prepare the slides. Let me just show you this. The first computer. Why? Why you need to have such kind of chips? In the past, humankind need to manually calculate almost everything. It's really time wasting, right? So we had a dream. Hopefully, something can help humankind to do automatic calculation. With calculation, you can do almost everything. Okay, even for speech recognition, right? Image processing, you need a lot of calculation. Yeah, calculation means almost everything. For example, for the drone control, right? The missile control, you need to calculate everything for your GPS, right? You get the signal from the satellites, you need to calculate where the car is, blah, blah, blah. So anything is related, even for AI. That is some kind of neural calculation. So from the very beginning, humankind hope we can speed up the calculation, yeah, to help us evolve almost everything. We have industry evolution, right? We have many kind of evolution, but calculation is the most. So this is the first computer. You can see Mr. Babbage. He created the first so-called difference engine, and after that maybe calculator. Okay, yeah, it had more than 25,000 parts because it is a mechanical one instead of electrical one. Okay, so it is bulky, it is huge, it is really heavy, and it cost a lot of money. Yeah, but at least he made it. He made some kind of prototypes. I have no idea it is functional or not, but at least it opens the door for humankind. We don't need to do calculation by our own hands. Machine can help us. And after that, years later, we have the first electronic computer to do the same calculation, even more complicated calculation. But that is with the help of electronics. So you can see, wow, this is the room for ENIAC. That is the, maybe it is created by IBM of somebody or some very famous company. You can Google it online. Anyway, wow. It is also really bulky because I guess the weight should be tons. Okay, and it needed at least 3 employees. Yeah, 1 man to plug in that, and maybe 2 women to help us type in the code. Okay, they don't have anything. How can I say? The original prototype should be very similar to the so-called typewriter. Okay, but we have the card. After you type A, B, C, D, right? You punch holes at different positions, and then the machine use some kind of optical mechanism to read the position of the holes, yeah, to understand what the code is. Okay, and after that, yeah, the computer, the so-called computer, can help you do such kind of calculation. Yeah, anyway, from such kind of mechanical, yeah, 1832, right, to electronic computer, humankind wait for more than, oh, okay, let me see. Wow, more than 1 century. But at least we make it even more faster, even more complicated than before. So since after, our dream changed from mechanical era to electronic era. Okay? But anyway, it's still too huge, too expensive, right? I think the size is much bigger. Okay? And how about the calculation capability? Much less than Casio calculator. All right? Don't expect your smartphone. Your smartphone is too smart than this one. Yeah, maybe millions of times smarter than ENIAC. But anyway, that is the first electronic computer. It opened another door for humankind. Electronic calculation. Much, much faster than the mechanical counterpart. All right? And after that, there was another dream. The dream lasts almost forever, even till now, and into the future. Miniature. How to minimize such kind of electronic computer? Because it's too heavy, it's too huge. It is not for everybody. Right now, everybody maybe has more than one smartphone, right? Without smartphone, you cannot do anything, yeah, in current society, right? But in the past, maybe it is from IBM. How many employees IBM had? Tens of thousands. They need to share such kind of bulky computer. It doesn't make any sense. So, again, it opens the door, a new door for humankind's electronic computer. But after that, we got another dream to minimize it. But how to minimize it? Because for such kind of calculation, it uses a lot of electronic components, just like vacuum tube. Okay, vacuum tube is really bulky. Right now, if you are interested, maybe some of the audio amplifier, yeah, traditional audio amplifier, I mean still in the market, yeah, with vacuum tube to amplify your audio signal, because some of the players they feel that the sound from such kind of vacuum tube is warmer. They have more feelings when listen to the sound amplified by vacuum tube instead of transistor. But anyway, I'm not such kind of audio player. Yeah, I hate it very much because it's bulky. It's really bulky, very huge. How to minimize the size? We need the help of the other devices. So, humankind created transistor to replace vacuum tube. Okay? You can see this. Wow, so many. Mr. Badin, along with the other two gentlemen in TI, Texas Instrument, all those three, they created the first transistor, okay, in 1947. This is the prototype. If you go to TI, nowadays, you can still, yeah, pay respect to the original prototype created by those three gentlemen. After almost 10 years, 1 decade, they got Nobel Prize in physics. Okay? All those three, they share the Nobel Prize. This one get 1/3. of the money, yeah, of the award. And after that, one of them, Shockley, he created the other. Oh, sorry for that. Wait a moment. Go away. Shockley, 4 years later, invented the other type of transistor, bipolar. Till now, we still use some of the bipolar transistor, but more than often, we replace bipolar with CMOS. Okay? And after that, you can see 5 years later, we have the first bipolar digital logic gate and Kilby, yeah, Jack Kilby created the first chip. Later I will show you. Okay? They are the other big guy in the IC industry. But anyway, that is only prototypes for commercial purpose. The first chip actually created in 1961 from Fairchild. Many of the engineers from Fairchild, they went out to open their own business, just like Intel, Analog Devices, blah, blah, blah. National Semiconductors. Most of the engineers or the co-founders, actually, they are from Fairchild. So the company is really fair to its own kids. Okay, it has a lot. After that, there were a lot of companies, even bigger than Fairchild. Anyway, maybe tens of years later, Fairchild has some kind of difficulty to the market, so it is bought by National Semiconductor, to my memory. Okay, so nowadays maybe you can Google online whether or not there is still any company called Fairchild, because I heard that National Semiconductor would like to spin off Fairchild again, but I have no idea whether or not they did. All right. And after that, we have the other one, digital chip. We call it TTL, transistor logic. I think you learn this kind of logic already from microelectronics. Okay, and then the even faster digital chips. We call it emitter coupled logic, ECL. But anyway, if you have no idea what is TTL, what is ECL, forget about it, because they are already no use for, especially for analog IC design. Even for digital chip design, I don't think we need it, okay, because they are too old. Yeah. Anyway, all those three gentlemen get the Nobel Prize, and the prototype I mentioned already is still in TI. If you go to visit TI, you can see the original prototype. It opens another door because we use transistor to replace vacuum tube. Transistor can be much smaller than vacuum tube. Okay, so this is a vacuum tube for ENIAC, and all the way down. Okay, the transistor becomes smaller and smaller and smaller. Yeah. But in the past, even with transistor, yeah, the transistor is much smaller in size than vacuum tube, but it's still discrete. I mean, one by one. Okay, so never mind how small the transistor could be. You need a lot of transistors, right, to complete the design of your circuit. It means what? The circuit is still too large. So we have another dream to integrate all the devices, never mind transistor, resistor, capacitor, everything on the same chip. That is the definition for integrated circuit. Integrate everything on the same chip. Okay, and this is the one. Jake Kilby. He had a dream, right? He served in the army after First World War or something. After his military service, yeah, he joined again TI. TI is really important company on earth for IC. There was a story that he's really young, 20-something, okay, to my memory, and he told his boss, I think we can integrate all those discrete components, I mean transistor, resistor, blah, 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 on the same wafer, on the same chip. Yeah, but his boss said, ridiculous. He didn't buy it. So maybe he would like to convince his boss. So during the weekend, he wouldn't like to play for fun. He went back to TI's lab to implement, to realize his dream. This is the prototype. He made it with transistor, capacitor, resistor, blah, blah, blah. Maybe 4 devices on the same chip. Yeah, anyway, if you are curious, you can get better detail, maybe through wiki something, okay? Anyway, he set 3 rules for the dream to open the door for integrated circuit. Yeah. Only semiconductor company can produce such kind of semiconductor. And all the circuit elements, including resistor, capacitor, can be made of a single one semiconductor. Blah, blah, blah. Yeah, anyway. So, it happened in the summer of 1985. Yeah, if you go back to the history, those gentlemen wait about 1 decade, I mean 10 years, to get the best award, Nobel Prize, right? How about this gentleman? In 1948, he created the first chip, first IC, right? But it's really sad. He waited for a much longer time. He waited for more than 4 decades to make it. In 2000, here, finally, he was awarded, okay? Again, the Nobel Prize in Physics on December 10, 2000. Wow, this is really amazing. So, the lesson you need to learn from the gentleman is you need not only to create something innovative, but you also need to live longer to get the award you deserve. Wow, it's really so. This is the photo for the Nobel Prize in 2000. If you get online to search, you can see this is the formal photo for the official site of Nobel Prize. He's really old in that era. Anyway, after that, humankind focused very much on MOSFET. Yeah, that is the mainstream tier now. We have another version, we call it FinFET, but that is originated from MOSFET. So you can see this. For MOSFET, in 1925, Canada, or 10 years later, in England, 2 different gentlemen, 2 different teams had the same idea, to fabricate such kind of MOSFET. Okay? But we have some kind of problem according to manufacturing process. So we waited for 25 years to make the first CMOS. CMOS means what? Both P and N, P-type and N-type. Okay? Yeah, but for mass production, you can see we have such kind of manufacturing problem. So even though we have CMOS as early as 1960s, but for true mass production, from the beginning, we had PMOS only. Yeah. Again, in 1960s, especially for low power calculators. If you have such kind of calculator from Casio, yeah, this Japanese company is very good at such kind of calculator. Yeah, with a coin battery, the calculator can operate for maybe 1 decade. Okay, it's really, really power saving. Why? Because from the beginning they apply PMOS only. But nothing is free. With such kind of very low power process, the operation speed is quite slow, right? So for humankind, we would like to speed up the calculation, right? So, MOS, yeah. MOS was applied for mass production instead to speed up the calculation in 1970s. And finally, in 1980s, humankind knew the secret how to integrate, how to manufacture both NMOS and PMOS on the same chip. That's it. Okay, but how? Okay. For example, if you have P substrate, you can fabricate your NMOS directly on P-type substrate. Okay? But how to fabricate PMOS on P substrate? No. Because if you have PMOS, your source and drain, P+, your body is P-. Sorry for that. They are connected all together. PPP, right? All those are P-type. So from the very beginning, your source and drain are connected already. That is the so-called depression type MOSFET. For our mainstream chip fabrication, we apply enhancement type MOSFET instead. Okay, it means from the very beginning, the source and the drain are isolated. They are not connected. Okay, only if you apply good enough voltage to the gate, they can be connected. That is the fundamental requirement. Okay, so how to make it? I mean, how to make such kind of enhancement type MOSFET instead of depression type MOSFET on P substrate for PMOS? Piece of cake. Right now, I think all of you know it already. With the help of N-well. Okay? In the substrate, in P-type substrate, we can fabricate N-well first, then PMOS inside. That's it. Because you have P+, and N-. Congratulations. This PMOS is still enhancement type. Okay? That's it. No secret. But humankind needs to wait for almost 20 years to make it. Wow. It's really upset. Anyway, since after the mainstream manufacturing for integrated circuit focuses on CMOS instead of the others, we forget almost about the others. This is the mainstream process for humankind. But if you would like to get better speed, nowadays you still have some not so popular process. Yeah, by CMOS, or gallium arsenide, or silicon germanium. Yeah, maybe we apply those for what? RF chips, especially for power amplifiers. Okay, but how about the core for your smartphone? They still use CMOS. Okay, yeah, that is the mainstream in the market. All right. But let me just show you the first commercial chip from Fairchild in 1961. Oh, yeah, this is the first, the photo, the mini photo instead of micro photo because it's huge enough. Maybe you can see it by your own eyes. Yeah, it contains 2 flip-flops. And then 2 years later, from the same company, from the same team, they not only reduce the chip size, but also integrate more devices from 2 flip-flops to 4 flip-flops. It opened another door for humankind. What kind of dream? Scale down. We would like to scale down everything. We will make it smaller and more powerful. I mean, more circuit on the same chip. That is the definition for scale down. Okay, so with the 2 chips, more than 50 or almost 60 years ago, that is the beginning of our dream to scale down everything. Not only till now, but also into the future. Okay? And let me just show you this. Intel, the dominant player in IC industry in the past. Nowadays, it is only one of the key players. But in the past, that is the dominant players. Anyway, it didn't make it by itself. Instead, through the help of IBM. That's it. Why? Because IBM created the first personal computer, IBM PC, right? From the beginning, it had 2 choices. One chip from Motorola, the other chip from Intel. For performance, Motorola chip is much better than Intel. I have no idea why IBM chose Intel, selected Intel. I have no idea. Maybe Intel provided much cheaper chips. Maybe. All right? So, learn a lesson. You don't need to be the best in the market, but you had a better be the cheapest. Okay? If you sell something cheaper than your than the other companies, your competitors, usually you can make it. Even though your performance is not the best, you can still make it. Yeah, that is a very sad but interesting stories, just like this. Okay, you have many kind of the other process in speed. They are much better than CMOS. But why we still have CMOS for the mainstream market? Simply because that is the cheapest. Okay? That is not the best. No, I mean in performance, CMOS is not the best. All those are much better than CMOS. But why we don't apply such kind of process for mass production? Oh, sorry for that. They are too expensive. They are too power hungry. They consume too much power. It is no good. Too much power, too much money, no good. Okay? Anyway, let's go back to this. After IBM selected Intel chips for its personal computers, Intel dominated IC industry for many decades. Till a few years ago, who defeated Intel to be the only one dominating the market? Up. Okay? Because Intel was too proud of its own CPU, x86. The series, that is from the beginning selected by IBM, right? till now still dominated our desktop, our notebook market. Okay, but it didn't pay attention to low power consumption industry. I mean mobile devices. For mobile devices, you cannot plug in your mobile device to the power system, right? It doesn't make any sense because it needs to be mobile. It needs to be moved from here to there. So we can only use battery for mobile devices, and it means low power consumption is the key requirement. Even though from the beginning, ARM's chip is much slower than Intel's, but after years of struggling, yeah, it defeated Intel totally for mobile devices. Okay? Does Intel have any kind of chip for mobile phones? Yes. But I think the percentage maybe less than 3 or 4. Okay? Yeah. I don't think even in the future Intel cannot make it for such kind of low power industry, low power market. No. ARM dominated the market already. Okay? Humankind cannot afford to turn our heads away, turn our heads back to Intel. No. Just like in the past, in the history, Motorola. I mean, for chip performance, Motorola chip is much better than Intel's. But right now, who knows Motorola? Many of the young guys, you simply don't know what is Motorola. In the past, Motorola is really a good international company. But sadly enough, the strategies were no good. Just as I said, the first problem is to compete with Intel. Its chip is much better, but maybe according to price or something, okay, it lost the market. And after some years, Motorola in the past is still very good for telecommunication. So it has a very crazy idea for global communication. It would like to put its own satellite around the globe for humankind to communicate with each other. Okay, the idea was really good, but too expensive. Okay, your mobile phone, satellite phone, need to communicate with the satellite. It means what? You need to go outdoors and to search where is the satellite. You need to point, your antenna to the satellite. Oh, where are the satellites? Far above into the sky, right? So the satellite phone needs to be very, very powerful. Otherwise, you cannot communicate with the satellites, right? It's really large. It's really power consuming, blah, blah, blah. So it failed. Anybody here know the company called Motorola? Motorola. Oh, it means you're not so young. Anyway, years ago we also have Motorola smartphone, right? But already out of the market, maybe more than 10 years ago. Oh, really upset. In the past, it is a very good company, but right now, peanuts in the market. Nobody in the market is really upset. So the other lesson you need to learn is don't make any wrong decision for the company. Okay? Otherwise, the company will, just like Motorola, from 1 to 0. Okay? Another bad example is, what is the phone from Finland? The best future phone company, Nokia, right? Nowhere to go for Nokia. It dominates the market for feature phones, but it's too successful for Nokia in feature phone market. So again, it didn't notice, it didn't pay enough attention to smartphones. All right? So it lost all the battleground to Apple, to Samsung, to even HTC. Okay? Anyway, yeah. Strategy making, policy making is more important than chip design. I mean, for companies. But anyway, you can see the tendency for the so-called scale down. In 1971, the microprocessor called 4004, yeah, it had only 1,000 transistors on the same chip. And you can see, wow, 4 millimeter by 3 millimeter. Wow, it's really 20 millimeter square. I think it is a huge chip in that era. After how many years? Oh, almost 30 years later, Intel made Pentium 4 microprocessor. It had 42 million transistors. Wow. Okay, that is our dream. You can see the chip size. From here to there, no much difference. Right? But how about the number of transistors? Wow. From 1K to 42 million. Bingo. That is our dream. Never ending. Okay. Allow me to show you the most updated one. I mean for CPU. This is the almost the best on earth, okay? In last year, TSMC helped Apple to fabricate such kind of mobile phone called A12 Bionic in TSMC 7nm process. Okay? Wow! It is so-called system on a chip. Apple integrates almost everything it needs for mobile phone, except for RF, because CMOS is not good for such kind of high frequency operation. All right? For all the others, from baseband to medium band, bingo. In one, on the same chip, system on a chip. We call it SoC, right? It has 8 cores. Right? Also, it integrate an improved version of neural engine to your speech recognition, especially not for speech, for facial recognition. Yeah, because in the past you need your fingerprint to activate the mobile phone, right? But nowadays you can look into your mobile phone. Yeah, the mobile phone you will know. You are the boss. Then you don't need to touch it, right? You can activate the phone. You can call it anyway. Who can help you? AI, neural engine. All right. Anyway, I would like to show you this amazing figure. How many transistors in 2018? Gosh, almost 7 billion. Okay? From 2000, here, 42 million. Wow, see? 7 to 7 billions. Okay? How much increase in transistor count? Almost 100 times increase, right? But anyway, this is not the biggest. If you are interested, okay, this is some kind of floor planning, and this is some kind of photo micro photo, okay, of the chip. And then, okay? Oh, sorry. Later I will show you. Here now, the largest chip actually is from Xilinx. Okay? On the chip, Xilinx, the largest chip from Xilinx, it has 50 billions. Wow. Compared to Pentium 4, only 42 million. It means what? Within 18 years, humankind increased the number of transistors by 3 orders. Right? From 42 million all the way to 50 billions. It's really amazing. But again, I told you already, the dream for scaling down is never be ended. Yeah, we are really hungry for what? For performance. We would like the smartphone to run faster and faster and to be more intelligent, to be smarter than before. Okay, so the tendency is we need to embed more cores, especially such kind of neural engines in the future. All right, so you can guess, oh, from MediaTek, in last year or 2 years ago, it has a 10-core chip. So you can guess, in the future, even for your smartphone, you have 20, 30, or even 100 cores. Yeah, it never be any kind of amazing thing to humankind because it already happened. Okay? Yeah, so what is the tendency for the so-called scale down? Yeah, the most famous one is Moore's law. Actually, Mr. Moore, Gordon Moore, is one of the co-founders for Intel. All right, and I told you already, in 1961, that is the first commercial chip on Earth, right? So after observing for only 4 years, Gordon Moore told everybody, yeah, his assessment, his judgment about IC industry, right? Only for 4 years of observation. He said what? The number of transistors on a single chip will be doubled for every 1.5 or 2 years. That's it. Okay? Till now, he's about correct. Yeah, the law, it is called Moore's law. Moore's law is, roughly speaking, Moore's law is correct. But why? Oh, simply because, you may guess, it is one of the co-founders of Intel. And Intel dominated IC industry for many decades. So I guess Intel pushed itself very much to fit the Moore's law. And since Intel is the leader, was the leader in IC industry, so humankind can follow the prediction of Moore's law. But a very sad story for Intel is what? Intel slows down very much for its 10 nanometer process. Okay, till now, it still have very big trouble with mass production in 10 nanometer process. So in last year, we have a lot of difficulty to get enough CPUs from Intel. But I mentioned already, even though right now Intel is not the dominant player in the market, but it still dominates PC market. I mean, for such kind of CPU, it still dominates the market very, very much. Till now, it has only one competitor called AMD, right? So the story changed a lot in last year. AMD in the past, just like Intel, they are called IDM, right? It integrates everything. They design their own chip, they fabricate their own chips, blah, blah, blah. But years ago, AMD changed its mind. It spin off the IC fabrication to be global foundry, cooperated with IBM. Okay, IBM is also very important for IC manufacturing. Even for Samsung, the technology for IC fabrication actually, I mean for Samsung, is from IBM. Okay? In international business, blah, blah, blah. The company right now, I think, is more software oriented than hardware. But it's still, it is still a key player in IC manufacturing. I'm not talking about IC design. It designs its own chip for servers. Okay? But in the past, it created many kind of good idea for IC manufacturing, especially SOI, silicon on insulator. The performance is better than CMOS, but it's more expensive. So again, the mainstream market still focuses on the cheap one, CMOS. All right? Anyway, in last year, the company called Global Foundries, spin off from AMD, announced that they wouldn't like to go further for 7 nanometer, maybe even for 10 nanometer now. They would like to focus on 14 nanometer and the other mature processes. That's it. Okay? So here now, there are only 3 companies, capable of the most advanced processes. I mean, sorry. The definition for Intel, because Intel was the big brother in the past, so its definition is much tighter than the others. To be honest, Intel's 10 nanometer in performance, I think, is equivalent to 7 nanometer processes from TSMC or Samsung. TSMC and Samsung, I think, for definition, they are almost the same. Okay? But much different from Intel. But anyway, for TSMC, the 7 nanometer process went for mass production in last year already, right? For 8, 12, and the others. From Qualcomm, Broadcom, MediaTek, blah, blah, blah. All the top IC design houses, I think, they had their chips fabricated by TSMC in 7 nanometer processes. Okay? Samsung tried very best, to attract the others with much lower fabrication fee. All right? Also for 7 nanometer. Much cheaper. But why? Very few companies went to Samsung simply because the yield is too low. So Samsung had one way out. It would like to focus on 7 plus. It means the performance is better than 7 nanometer. But how? Through the help of ASML. ASML is the best for, how can I say? For such kind of light exposure. Okay? When you expose your chip, the chip you need to cover with photoresist, then cover with the mask, and then expose to the light, right? For such kind of lithography, okay, sorry for that, to expose to the light, to fabricate everything, we call it lithography, okay? For such kind of lithography, ASML is the best in the market, even much better than applied material than any of the other companies on earth, and it goes for extreme UV light. That is the best, but very, very expensive. So what is the strategy for Samsung? Samsung from the beginning bought almost all EUV lithography machines from ASML. what ASML could produce, Samsung bought all. That's it. For what? To stop TSMC. Yeah. When going the market. Okay. It buys all. Nothing for TSMC, right? Luckily enough, ASML tried to enhance its production for such kind of EUV machine. So I heard that because each year it can only produce around 20, but to the end of last year or in the beginning of this year, it is increased to 30. Okay, and TSMC decide to buy 70% of all the equipment. Okay, so no worries. Yeah, such kind of trick played by Samsung, I think, will become useless. Yeah, because right now, TSMC announced that they will get enough EUV machines to fabricate the 7+ nanometer chips, maybe before the end of this year. Maybe to third quarter or first quarter of this year, TSMC will push 7+ nanometer for mass production. Yeah. Anyway, to make a brief conclusion here, after Intel loses its market for such kind of process competition, right? Because even for 10 nanometer, it still have very huge problem for mass production. And AMD, since Global Foundry announced that they wouldn't like to go further, right? So AMD got the right to turn its head to TSMC. In the past, no, because they signed a deal. Global Foundry was spin off from AMD, right? So supposed to be all the chips needs to be fabricated, especially important chips, GPU, CPU, need to be fabricated by Global Foundry. But anyway, Global Foundry figured out it couldn't compete anymore with TSMC, Samsung, or Intel in such kind of luxury processes. It abandoned the market, right? So AMD announced its first 7 nanometer chip for its CPU or GPU to the end of last year. And in this year, they will go for, again, 7+ nanometer process. Hopefully, AMD will get more market share from Intel. It will open a better future for consumers because Intel's CPU is more expensive than AMD's, right? And right now, AMD's 7 nanometer CPU, I think the performance is about the same with Intel's 14 nanometer because that is the new design for AMD. Yeah, it takes time to improve the performance and also the structure. Okay, if the performance is only enhanced by new processes, yeah, you cannot expect too much. All right. So not only to apply TSMC's best process, but also AMD needs to modify its own structure, yeah, to fully defeat Intel's chip in performance. It needs to. Okay. So you can see the evolution of such kind of many kind of chips. For example, DRAM. Yeah, from the beginning here to there. 80 years ago, humankind, how can I say? You can see, from the very beginning, one DRAM chip can store 1 page of information, okay? And then here, 1 book. And then in 2001, almost a whole encyclopedia. Wow. And how about here? Almost our humankind memory. 80 years ago, right? 1 chip is capable of to contain all your memory, all your DNA information. Wow. It opens another door for humankind. Yeah, because almost everybody hate to pass away, right? We hope we can live forever. But how? For your body? No. But how about for your thinking, logic thinking? Maybe. Yeah, before passing away, we can store all the information to your mobile phone. Then the AI for yourself will call your kids, your grandkids, when necessary, to communicate with them, to teach them everything you don't have time to do, right? That is a real, I think maybe it will happen. It is not only some kind of fake story. No, I think it will happen very soon in the near future. Okay? And this is that is for DRAM, right? Let's have a look at CPU again. Maybe it will by purpose follow the prediction of Moore's law, right? So you can see that the tendency of such kind of a number of transistors on the same chip, really fit the prediction of Moore's law. But how about 10 nanometer? No worries. TSMC and Samsung help Intel to keep the promise according to Moore's law, right? But right now already 7 nanometer plus. TSMC said maybe in next year 5 nanometer will go for mass production. And then maybe I heard that 3 nanometer was already on some kind of test run. Okay, risky run anyway. But how about the process after 3 nanometer? Right now, nobody knows. All right? So, will Moore's law go further? Maybe not. Till 7 nanometer. Humankind need to figure out, need to find another way to expand our territory in IC market. Okay? By such kind of very simple scaling down, two-dimensionally. No, I don't think. I think 3 nanometer may be already the dead end for Moore's law. I mean for two-dimensional chips. So it means what? We need to go chip fabrication three-dimensionally. Okay? From 2D to 3D. Yeah. Maybe that is another way we can help Gordon Moore to keep his promise. Yeah. What is the promise? The transistor count will be doubled for every 1.5 or 2 years. Hopefully. So this is what I told you. The Wikipedia shows transistor count. If you are curious about how many transistors on a chip humankind can have, allow me to show you this. Wow. Yeah. Last night, I reviewed the slides and modified some of them. Yeah. This is the most updated figure I can show you. Till now, this is the biggest chip. Oh, the definition is the most number of transistors. Okay, how much? Wow. In last year, Xilinx make it through the help of, I guess, TSMC. Okay, with again 7 nanometer process on a single chip. Humankind can already make 50 billions of transistors. Wow, it's really amazing, right? But you need to be careful because for such kind of huge chip, in theory, only one transistor fail means you need to drop the chip, right? It doesn't make any sense. So it has a lot of spare parts. During testing or auto testing, yeah, they can replace the broken ones with the spare parts. Otherwise, I can promise you, with such kind of huge chip, the yield is almost zero. Okay? Yeah. So, it is for your own future. It is not only good for IC design, but also for such kind of spare part design, IC testing, blah, blah, blah. Almost everything. You have a lot of ways to secure your own future. But you need to be very careful. AI. Okay? Please keep this in mind. If what you learn right now, or in the university, on campus, all those are likely to be replaced by AI. You had better don't touch. Okay? So what I'm talking about, digital design is more likely to be replaced by AI than analog ones. Okay? Right now you can see some AI program can help us to produce codes by itself. Okay? But did you ever heard any kind of AI program can help us to produce any kind of analog circuit design? No. Luckily enough, maybe in the far future, maybe it will happen. But I promise you, digital design is more risky than analog IC design. Why? Due to AI replacement. Okay, so again, not only for analog IC design, you had to better figure out what classes you take, what kind of research you have in your lab. Think about it. If it is more likely to be replaced by AI, then you had better turn your head away to find the other supervisor to take the other classes. Okay? So, the best class I recommend you to take is AI, because AI will replace almost everything in the future. Okay? That is your future if you join AI. Otherwise, you will be replaced by AI in the future. That is really, really upset. Yeah, that is the transistor code. It goes up almost all the way, right? Yeah. And how about the die size? How about the wafer size? Oh, it's really hard to grow, to expand not only the die size, but the wafer size. Nowadays, I think for mass production, the best is 12 inches, right? Maybe a few years ago, humankind were talking about future of mega fab with 18 inches. A few years ago, people said there were only 3 companies capable of such kind of investment. Again, Intel, TSMC, and Samsung, right? But right now, if you listen to them, I think nobody mentioned about this again. Too expensive. Okay? So, even for the most advanced processes, just like 7 plus, 5 or even 3 nanometer for test run, all focus on 12 inches wafer. So it means what? 12 inches wafer already existed on Earth maybe for 2 decades, I guess. Okay? It doesn't grow bigger because it's really hard. So how about die size? The same. You can see the slope for the increase of die size is only a few % per year. Okay? Now, it won't be doubled. See? It won't be doubled for 1.5 or 2 years. No, forget about it. Yeah. On average, around 7% increase in die size. Okay? Good enough. Yeah. So, it grows. It is doubled. Maybe only in 1 decade. Okay? Not so fast. And how about the frequency? In the past, it goes up. Then, slow down. For what? Power consumption. The chips became too hot to be useful, right? So Intel and the other companies try their very best to reduce the power consumption, but still keep the same performance or even enhance a little bit in performance. After that, we know the way to reduce the power consumption and then go all the way up for such kind of frequency. But you can see that in 20-something, it already reached 1 gigahertz, right? Here now, if you look at the operation speed of all the luxury chips, I guess the maximum is still around 3 to 4 gigahertz. Humankind cannot afford to go further. Why? According to power consumption. Okay? We cannot go further. But again, humankind are hungry for performance. What you can do? More cores. That's it. You cannot go faster, then you need the help from your friends, right? You had better get more friends to cooperate, to co-work for humankind. That's it. More cores. Right now is the only way out for performance enhancement instead of increase in frequency. So I promise you, the operation frequency was already saturated more than 1 decade ago. Okay, saturated at around 3 to 4 gigahertz. That's it, no more. Yeah, power consumption, power dissipation, as I told you. Yeah, it is limited, I guess, 100 watts, already the maximum. It is already saturated. Okay, and then if you look at the power, it is a major problem. As I showed you already, here, right? Why? Humankind, during some years, we cannot push the frequency higher simply because too much power consumption. Okay, till now, power consumption is still a big problem for humankind because we hope we're not only hungry for performance, but also hungry for what? How much hours you can use for one charge, right? We hope you can charge the mobile phone, such kind of powerful mobile phone, one charge for 1 week, wow. Or even for 1 month. Okay, if you can make it, you will defeat all the others, including Apple, right? But anyway, Apple, Samsung, all the smartphone company, they try their very best to either enhance the capacity of the battery or reduce the power consumption of the chip. That's it. In 2 ways. Everybody compete with each other. So, if you would like to know how big the problem is, allow me to show you another figure. We call it power density. It means what? How much power the chip will consume per chip area. For example, per millimeter square. How much power you can waste, you can dissipate. Okay? Let's see it in the past. And all the way to the future, right? So, how much is this? To help you get better understanding what kind of power density our chip, especially our CPU, is, allow me to show you this. For P7 or P6, the power density is already similar to hot plate. If you go to barbecue, right? Go to some kind of restaurant with hot plate, you put the meat over the plate, within minutes, it will be fully cooked. So don't use your finger to touch such kind of chip. Yeah, you will cook your chips within minutes. Oh no, within seconds. You will burn your fingers. So we need a lot of powerful fans to cool down your chips, right? But things goes even worse. After that, how about here? If we keep on going for such kind of power density, yeah, it will behave like a nuclear reactor. I mean, according to power density, how much power you can generate from nuclear reactor will be similar to how much power you will dissipate for your chip. It doesn't make any sense. Too much, right? So that is the difficulty, power density. And you can see that. Why I have dash line here? Because it is impractical, right? So right now, I can promise you here, 1 watt per millimeter square, I think that is the most. Okay? Not per centimeter square, but because if you look at the chip size, right now, a few tens millimeter square. And how about the power consumption? Around, I told you, 100 watt, right? So right now the maximum for power density is around 1 watt per millimeter square. That's it, no more. Okay? Because power dissipation, heat dissipation, is something related to mechanical instead of electrical research. Electronic go much faster than mechanical. Okay? If you go to the classes of mechanical department, you will see most of the classes help the students to learn knowledge a few hundred years ago. Okay? But for ours, sorry. But for ours, I told you already, we publish papers for new technology, new circuit, new process, almost every paper per minute, okay? Or even a few seconds. So our evolution, I mean in electronics or in electrical field, our evolution is much, much faster than the others. Never mention about mechanical, such kind of very traditional field. And for such kind of power density, the limitation is how to dissipate the heat. If the power density becomes too much, it is the mechanical issue instead of electronic issue, right? So you can see mechanical guys, they didn't do good enough job for such kind of heat dissipation. So we are limited to 1 watt per millimeter square already. Okay, no more than that. Till now. And this is the power density. Yeah, see? Bingo. That is the statistics till 2010, even till now. The saturation line is here, right? How much? 1,000 milliwatts. It means 1 watt per millimeter square, right? I don't cheat you. I don't cheat you. That is the ugly truth. Yeah. Not only for chips, but also for the whole devices, just like the microprocessors, the mobile phones. Wow. So this is a very good slide for you. Why? Because that is the demand for humankind, for consumers. They need more performance. Okay? But anyway, how about IC designers? Sorry for that. We can enhance our productivity for IC design. Why? Because we we get better EDA tools, especially for digital ones. Okay, and then we get more knowledge than before. So gradually, humankind can enhance our design capability, right? But the rate for such kind of increase in design capability is much slower, much less than the rate for humankind's wish. Okay? So it means your future is secured. That's it. Yeah, because we have more demand than supply, than what IC designers can supply to the market. But I need to warn you, this gap will be narrowed down by what? AI, especially in digital field. Okay, so this is the good reason for me to convince you the class analog IC design deserve your learning, your attention, because till now it's still very hard to replace any kind of hard work by humankind for analog design. It's really, really hard. Okay? Yeah. It is some kind of roadmap from SIA, Semiconductor International Association, blah, blah, blah. Okay, from SIA, you can see. Yeah. To my own experience, the roadmap from SIA was always lag behind the real situation. It means TSMC, Samsung, Intel, they always go further than the prediction, than the roadmap predicted by SIA. So this is only for your reference. The absolute value is not correct, okay, because we can go faster than this. Anyway, the tendency is correct, right? The feature size will be reduced, yeah, year by year. And the power supply, the voltage for your power supply will be reduced year by year. That's it. But this is only good for digital one instead of analog. If you would like to design any analog circuit operate at 0.6, even in 2014, even right now, to design a complete analog circuit operating at 0.6 volt, I think it's still something related to mission impossible. Maybe some of the circuit can operate at 0.6, but not all. I mean for analog. Okay? And this is the reason why, even for 7 nanometer, I promise you, they still provide some thick MOS that can operate all the way maybe to 1.8 or even 2.5 volt. That is so-called analog friendly device. Because for analog 1, 0.6, never mentioned about 0.9, is still very hard. How about 0.2? Not so easy. Okay, 0.5, 0.8, piece of cake. That is the ugly truth for analog design. If you would like to push it further, I mean to lower down the supply voltage, it is only good for digital circuit, not for us. Sorry for that. Okay, many of the excellent, good analog design still depends on large supply voltage. If you lower down the voltage, many of the good circuit, good analog circuit cannot survive. Okay? So if you would like to integrate everything on the same chip with such kind of good process, sorry, for analog design, you cannot use the regular MOS. Okay? I mean, the thickness of the gate oxide needs to be much more than the regular MOS for this one. Okay? That's it. Yeah. So we need somebody really talented to modify the structure of our analog circuit. Otherwise, we cannot make it. Right? That is the roadmap for you to refer. Yeah, scaling trend. Remember for DRAM, MPU, CPU, and VDD all the way down, but for digital circuit, not for analog one. Later, I will have another figure for you. Okay? Yeah. The trend is correct. The cost per transistor becomes lower and lower, becomes cheaper and cheaper. That is our very set life. For all the electronics, right? The price is always going down, right? Just like this is iPhone 7 Plus. I bought it a few years ago with 35,000, more than 30,000 NT dollars. Right now, for a brand new one, I think the price maybe is already 50% off. Yeah. Anyway, that is our very sad life, because the price for the same product is always going down. So how can you survive? Can you provide even cheaper than this? And if you would like to do business in this way, to provide cheaper and cheaper products, it means your margin for profit will be reduced substantially, and finally the company will go bankruptcy, right? It doesn't make any sense. So the way makes more sense is you need to create, you need to design new products with better performance. Then you can keep the price. That's it, right? Because the price is always going down. To keep the price means what? New design with better performance. That's it. And this is the reason why iPhone or Samsung phone, any kind of phone, they need to have new versions each year. Yeah, to keep the same price. Apple made a serious mistake in last year, because for new versions, the price was still going up, right? But the market was going down. Then it had a very miserable result for the market share. Yeah. So how about this year? I think all the smartphones, new smartphones, will get lower price, I guess, from iPhone, from Samsung, from everybody, because the market right now is really bad. Okay? And this is another slide for you to refer. You can see this is for CMOS. According to performance, operation speed, BJT, gallium arsenide, they are much better than CMOS. But why we focus this for mainstream market? Simply because it is the cheapest. Good enough. That is what I said. Okay? Why? We would like to scale down all those chips, all those processes, because for definition, to scale down the process for each generation, the length, the feature size needs to be 30% off. Why? Because for area, that is width by length. Width 30% off, length 30% off. So, yeah, 0.7 by 0.7 equals what? Almost 50%. So that is a formal definition. For each new generation for IC fabrication, the size of your device needs to be halved. 50% of the previous generation. Okay? With such kind of scaling down, it means that for the same chip of the same area, you will have 2 more times of transistors. Yeah, more likely you will have 2 more times of functions to fit the need of your hungry consumers. Okay, that's it. We would like to get more function, more performance, and also the cost, in theory, will go down. I mean, per transistor. Yeah. But again, I told you already, to cost down is not a good solution. You had better keep the same cost, but you integrate more transistors, more functions to keep the price the same. Okay? That is the best. So, what is the major challenges for your own design in the future? We have two aspects for you to refer. If you look at the challenges in microscopic, I mean bottom up. You do the very detailed design from the bottom to the top, right? So you need to pay attention to the speed. The speed needs to be as high as possible, and you need to have better to reduce the power consumption, right? And also you need to pay attention to especially low supply voltage design. That is very, very important but hard. Okay? Yeah. And the routing becomes more complicated than before. So how to reduce the parasitics? That is also very important. And how about to deal the noise, the crosstalk? How to make sure your chip fabrication will get good enough yield? It means reliability, right? And design for manufacturing, that is also very important issue. Your design, if your design fit the manufacturing, it means after fabrication the yield will be high, right? Otherwise, your design is really hard to fabricate. Oh, sorry for that. The yield will be really low. And how to distribute your clock, blah, blah, blah. You need to pay attention to every kind of detail. That is the microscopic issues. But anyway, even though you make it, you will still have many big problems. Why? Allow me to show you. This one. Macroscopic issues. First of all, time to market. Even you make it, I mean for the design, oh, you take all the details, you make it very good, with very good performance, very good blah, blah, blah. Oh, but it's really late to enter the market. You will be still out of the market. Okay? So, according to time to market, yeah, this is a very good example for smartphone. In the past, we have only feature phones. The best is Nokia, right? And after HTC, a Taiwanese company, I guess it is the first to really integrate everything into the phone, to make it smart, to make it intelligent. HTC was the first. Anyway, for a smartphone, the market looked like this, right? Maybe it will go down in the future. Hey, who knows? HTC here, no good. HTC, I think it will out of the market very soon, very, very soon, because it lost a lot of money in recent years. I don't think it will survive for a long time, no. But it is the first, right? According to time to market, too early to enter the market is still no good because the market size is too small to get any real benefit. Okay, so what is the best timing to get into the market here? Right? Before the booming, the size of market increased very much. Who made it here? Apple. So here now, Apple still makes the most money from the market. Okay? To last year, for the most updated statistics about a smartphone, to my memory, for market share, Apple less than 20%, maybe only 14 or 15. Okay? But for profit, Apple made more than 80%. And how about the second one? Samsung made more than 20%. It means what? The first and second altogether make more than 100% of profit. Means what? For all the others, they are simply losers. Okay? But anyway, you say, hey, we have a Huawei, we have Zhongxin, or anyway. Okay? Some of the companies, they still make money, right? They still make money. It means for all the others, they lose a lot of money. That's it. Okay? So top one, Apple. Top two, Samsung. They get more than 100% of the profit. Wow, it doesn't make any sense. Again, time to market is really important. To be here, it means what? The design need to be pushed earlier, right? So as the manager of the design team, you need to estimate how good your team is, right? So time to market is a very important issue for the managers to design, to concern. Okay? If you go too earlier for the design, then the time to the market will be here. If you go too late, then the market, the time for you to enter the market is there. Oh, that to enter the market here or there, both are really bad. Because here, the market is already to be saturated. No more to get the market share. So, who will be the winners here? The top one, the top two, blah, blah, blah. Winner takes all. No space for the rest. Even you can see for Taiwanese company, Acer, ASUS, they are really good in IT industry. They are really good at desktop notebooks, but they simply lost their background to mobile phone. Okay? Acer already, years ago, already announced abandon the mobile phone market. Don't touch. Okay? It's really sad. And how about ASUS? I guess ASUS will also out of the market very soon. I mean for mobile phones, because ASUS phone, Zenfone, blah, 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 the market share is too small to be beneficial. It doesn't make any sense for the company. They had better go back to focus on their own desktop, notebook, blah, blah, blah. Oh, Acer actually, it find another way out for gaming. Gaming notebook, gaming desktop. So, it made a lot of money for such kind of gaming industry. So they both, Acer and ASUS, they both enter the market too late. Okay? Anyway, I think most of you wouldn't like to be only engineers in the future. For engineers, yes, you focus on these microscopic issues, but you need to focus on this. And also you had better learn both sides. I mean, you had better know how to design analog circuit and the both, digital circuit. For analog IC designers, you need to be very outstanding for analog design. But you had better know something about digital design, because there will be only one team leader, right, to integrate both analog and digital. So the leader is supposed to know both sides. Okay? Yeah, so this is another recommendation from myself. Don't only focus on analog IC design. You had better know something about digital. Even though digital will be replaced, more likely to be replaced by AI in the future, but you had better still know something about it. Or you had better know something about AI. It will be even better. And then, how about the others? the design complexity. Because if you are the leader, you need to know how much complexity and how capable your team members are. Then you can estimate the time to market, right? That's it. Yeah. And for digital design, to speed up the process, we have high levels of abstractions. Later, I will show you what is abstraction means. And hopefully, we have some IP can be reused, can be portable from this process to that process. So for ARM, piece of cake, right? Each time TSMC announced the newest process, how to convince Apple, Qualcomm, and all the other companies to use such kind of new process? Very easy. TSMC usually co-work with ARM to fabricate the first ARM chip with the new process. So I guess for 7+ nanometer process, TSMC will announce a new ARM chip in this process to the market to convince everyone. Look, but only one core, okay? One core good enough. Look, I fabricate one simple core from ARM with the new process. Then Apple, Qualcomm, they will follow. TSMC friends told me for each new process, they need not only to show a prototype from ARM, but also after the companies would like to have chips fabricated, designed with such kind of new chips, they still need to teach the layout engineers for the other companies how to do the layout for the new process. Okay? Yeah. So layout is not so easy as you guess. No. Especially for most advanced processes, the layout pattern is really, really ugly. Yeah. One story is that for A10 or A9, right? For maybe 14 nanometer or 16 nanometer process, Apple decided to use TSMC process, but after that, Apple figured out, wow, the chip size is much larger than before. TSMC said, no way, what's going wrong? So TSMC sent a team to Apple headquarters to check the whole design, and finally they found the layout pattern was totally incorrect. Okay. After that, TSMC sent some layout engineers to Apple headquarters to teach the layout engineers how to do a good enough layout. I mean, to reduce the device size, the device area. That's it. Okay. Since after TSMC would like to provide much better help for the other companies to attract them to use such kind of new processes. Especially TSMC's process is the most expensive one on earth. Okay, so it needs to convince all the companies it deserves their money. They have something to coach the other company, even for layout. Okay, so you can see for each process, TSMC design through the help of ARM. They design the first chip. And then they do the first layout, definitely. After that, they need to teach the others to follow their layout patterns to reduce the chip size. That's it. Okay? So the tendency is also good for you to refer. The staff cost increased substantially, especially for analog IC design. It means if there's anything wrong with IC design houses, usually they file the new ones, okay, instead of the old guys. The experienced engineers, it means some kind of property belonging to the company. They would only like to fire the new engineers instead of the old ones. On the contrary, for digital company, digital IC design company, usually they fire the middle one. Okay, the manager here, the new here. The new engineers means lower pay, right? So they fire the middle class. That is totally different. For analog IC design houses, they fire the newest. So the longer you stay in the company means, yeah, the more value you will become for the company. Nobody would like to fire you. Okay? So experience is is more important in analog domain than in digital. And why? One of the reasons is EDA tools. EDA tools for digital design, it is too friendly, yeah, too intelligent. So for digital IC designer, they don't need to touch the detail. No, they do their own design through coding. Just very similar to writing C++ program, right? You just describe what you want, good enough. So we call it VHDL. VHDL, very high level description language, blah, blah, something like that. Okay, but the other more popular version, we call it Verilog. Yeah, much similar to each other. VHDL, Verilog. After you write the code, some EDA tools will help you to synthesize the circuit, and the other tool will help you to do placement and routing. If there's nothing wrong, you can go for fabrication. Okay? After APR, automatic placement and routing, you can extract all the parasitics to do post-simulation. Okay? For digital circuit, if post-simulation says yes, after fabrication, the result is always yes. It's usually. Okay? But how about analog IC design? Sorry for that. Even your post-simulation says yes, yes, yes. Usually after fabrication, they will say no. That is really upset. So how to narrow down the gap, the performance gap between post-simulation and fabrication? Experience, know-how. All right? And how to gather good enough experience, know-how? Doing by learning actually is really bad in this field, because on campus, how many batches you can have for your master degree? 3 to 4, right? After you design something, you need to apply for fabrication. Maybe after 3.5 to 4 months, you get the chip, measure it. Something wrong, right? You need to redo the design for a few months. Then apply for another fabrication. Again, you need to wait for 3 to 4 months. So how many 3 to 4 months you have for your master degree? Very few, 3 to 4. Okay? So how much experience you have? Very few, because usually you focus on the same circuit. For the first design, it failed. For second design, it failed. If you are lucky enough to the final, you make it. That's it. Only one circuit, 2 to 3 years, right? So the knowledge gathering in analog IC design is quite slow than in digital domain. My recommendation is you need to be very humble. Okay? You need to pay respect to your seniors, to your supervisors, to your leaders, your bosses in the company. Then for all of them will say, look, the young man looks so humble. He or she would like to learn, right? I would like to help. If you are really proud of yourself, I am from the top university, I'm really outstanding. Your EQ is no good, right? Nobody would like to teach you. You need to learn by yourself. No. in analog IC design, I promise you, you will fail very soon. Okay? Learning by doing is never a good way for analog IC designer. All right? You had better learn from the others, your seniors, your team members, your bosses, your leaders. Okay? Who would like to teach you? Only if you have good personality. So, in this domain, EQ sometimes is more important than IQ. Yeah, believe it or not. Okay? And then, if you focus on cost, there are two kinds of cost. One is NRE, non-recurrent. The other one is recurrent. Recurrent means what? For each batch, the more chips you want to get, the more money you need to put in, right? That is the so-called recurrent cost. For example, fabrication. You tell TSMC, I need 2 batches, I need 100 batches. Oh, from 2 to 100, then you need to pay 50 times more for fabrication, right? That is the recurrent cost. But what is non-recurrent cost? For example, design. For Apple team, design A12 after they make it once for all until A12 is out of the market. All right? They say, hey, they need to have new design. Oh, new design for A13 instead of A12. So for each generation, the R&D cost usually is only once. All right, and after that, especially, so the design cost is for engineers, right? The other one is also very, very expensive, mask. Oh, anyway, mask to TSMC. I heard that last time I tried to Google. I had no exact value for such kind of cost, but I read some news. Some of the companies said to get manufacturing, to get production from TSMC 7 nanometers, it needs to prepare. See how much this is in US dollars? Okay, 300 million US dollars. Oh, okay. For the overall, okay, it's a big money. The mask for fabrication becomes really, really expensive for newest processes. It means very few companies on earth can afford such kind of big money. Again, according to globalization, right? Winner takes all. So you had better to be the winners instead of the losers. Otherwise, in the future, your lives will become really miserable. Okay? Yeah. Okay, we try to integrate everything. That is the so-called system on chip. ROM, DRAM, DSP engine, right? Even AI, AI engine, a lot of that. If we cannot make it two-dimensionally, we need to make it three-dimensionally, all right? And this is also one of the reasons TSMC defeated Samsung in the past. Once upon a time, Samsung was the single vendor for Apple to fabricate maybe A9 or A8, I forgot, all right? Why? Simply because Samsung was the best for 3D chips. Yeah, it learned all the secrets to stack up all the chips, right? For what? To reduce the overall chip area. If you would like to integrate everything according to Moore's law, wow, the chip size needs to be very huge, and it is no good for our mobile device, right? So, since we cannot expand the chip with more function horizontally, then we need to make it vertically. Okay, and that is the so-called 3D chip. With the knowledge, with the best knowledge a few years ago in the market, Samsung made it for a single provider for such kind of Apple chips. But the yield is no good. The performance is also really bad. The power consumption, the operation speed were no good. So, to the health of the chip, to the rest life of the chip, A8 or A9, yeah, TSMC was invited by Apple to produce the other 50% of the chips. For Samsung, they claim they use 14 nanometer process, TSMC 16 nanometer process, right? As of application, TSMC's chip, yes, is a little bit larger than Samsung's. So if you open the cover, you will know which chip you get, okay? But even though TSMC's chip is a little bit larger than Samsung's, the power consumption is much lower, and the performance is a few percent better, all right? So consumers argued very much, especially in United States. If you figure out your iPhone is made of Samsung's chip, you can ask Apple to replace a new one, yeah, with TSMC inside. Okay, so after that, Apple learned a big lesson. Don't make such kind of trouble, since after it only choose one vendor, I mean for chip fabrication. Till now, TSMC is the only one. Okay, but why? TSMC can get back all the market from Samsung, especially for Apple chip fabrication, simply because nowadays TSMC provide the best and also the cheapest 3D packaging. All right, that is a very key technique for TSMC to defeat Samsung. TSMC not only defeats Samsung in fabrication, but also in packaging, 3D packaging. All right, so it makes sure it secure the market leader for TSMC through both ways. Yeah. And how about the market for system on chip? It's quite huge, especially for 5G. It is said that for today's BBC News or something, for ARMS, till now they already deliver maybe 8, from the beginning till now, for more than 10 or 20 years, it delivers almost 800 million to the market, right? Licensed to the other company, blah, blah, blah. And it is said that for 5G, we need 500 million more. Okay, how big the market is, you can guess, all right? So this is also another good lesson you need to learn. You see, that is the photos of very old feature phone. The front side, the back side. You can see a lot of devices, but more than 20 or 30 years ago, Berkeley Wireless Center, they designed a single chip to replace all of them. It means what? You had better join this. Don't go to such kind of discrete component company. If you fabricate many of the discrete components here, we will lose the market because humankind will integrate all in one. Okay? All devices on the same chip. No market for the others. Yeah. Never mind, you would like to join IC design, analog IC design or not. At least you don't choose such kind of companies for your own future. I mean, if their product will be integrated to the same chip, forget about it. Okay? Yeah, so what kind of devices we need to integrate? Almost everything. From, for example, for our smartphone, this is the antenna, right? From the receiver side all the way to the transmitter side. You can see from the very high frequency all the way after ADDA, we have the baseband, fully in digital. And it occupies maybe more than 90% of the chips. Okay? But anyway, what is the bottleneck? Usually not here, usually there. Okay? So even though we only occupy tens of percent, much less than 50% of the chip area, but we are usually the bottleneck. For example, in Intel, the dominant player in the past, it recruited more than 50% of analog IC designers instead of digital ones. Okay? It's really amazing. For Intel, the CPU maker, producer, they recruit more than 50% for analog design. It means what? Those are more difficult than this. That's it. Okay? So that is the big difference. Some example for you to refer, you can see, for the chip from Intel, you can see the yield becomes much lower. Why? Because the die size becomes larger and larger. And the die cost becomes sky high. Don't believe in the absolute value, but the tendency, the trend is correct. Okay? That's it. Because this slide is from Intel. It would like to convince us, the new chips deserve more money. All right? But after the competition from AMD and right now from ARM, some of the notebook, right now I think, are equipped with ARM chips. So Intel cannot sell the chips as high as it would like to have. All right? So don't believe in the absolute cost, but the tendency is correct. That's it. For larger chips, the yield will be lower, and supposed to be the cost will be higher. That's it. Okay? All right. That is a brief introduction to analog design. Yeah. And in next week, I would like to help you. Today, only for concept. And next week, for circuit. Brief introduction for analog circuit design. And hopefully, if you would like to stay in the class, hopefully, you can understand my English. Okay? If not, again, I recommend you to drop the class. You have no other better choice, but leave the class to the other professors. Teach the class in Chinese. Thank you all.